Now, while we discuss the static inventory problem under risk in the previous lecture sessions, so you might have noticed that we have the classified the problems under 4 categories. In the first category, what we consider, that is, the constant demand and the constant lead time. So usually, for the static inventory problem, it is not coming under risk type of problem, because both the important variables are considered to be constant, and this is not considered as an inventory problem per se. If at all it is considered to be a problem, then maybe you are dealing with multiple items, and if you deal with multiple items, and for each item you have this constant demand and constant lead time situation, so it is essentially a scheduling problem. Now, the other the two problems we have already discussed, that is, we have already mentioned, that is variable demand, constant lead time, and then the constant demand, variable lead time. Okay. So essentially, again, when you try to formulate both the problems, you will find there are a lot of similarities between in this in these two types of problems. Now we move to the fourth one, that is when you consider both so the demand as well as the lead time as a variable. So during this lecture session, I will give you an illustrative example of variable demand and variable lead time. And the next, what we try to do, that means we will refer to the types of mathematical formulations which you may adopt, which you may use in case the demand distribution is of continuous type, like say normal distribution or say exponential distribution. So let us first take up one numerical examples related to variable demand and variable lead time. So what you need to do actually, that means you need to provide the joint probability distribution. Like if it is a Q systems of inventory control, obviously you need to consider the demand during lead time. So during demand during lead time is considered to be a separate the random variable, and so you must know that the knowing the distribution of demand and the knowing the distribution of lead time separately, how can you determine the distribution of demand during lead time? So this is also referred to as one example of joint probability distribution. So let us first talk about this numerical example. Now, from the distributions given below, determine the lead time demand probability distributions. Okay, so that is your goal. What is the reorder point for a probability of stockout of 0.20? Okay, so once the joint probability distribution is known, then can you answer to the second question, that is, what is the reorder point for a probability of stockout of 0.20? Now here what you find, that for the given item, the daily demand in physical units, the notation is capital D. So the daily demand could be 0, that means no demand at all. There could be demand for 1 unit, or there could be demand for 2 units. Okay, so this is just an illustrative example. So at this stage you must thoroughly understand the concepts behind say the inventory control systems, the formulation, and solution, problem formulation and solution. So we are proceeding the stepwise, and from the past data, that means we, through analysis of the past data or from the frequency counts, we specify the probability values for all the demand units. So we are assuming at this stage that these probability values you have obtained from the frequency counts. That means these are considered as objective probabilities. So the demand is 0, corresponding probability is 0.30. That means 30% of the time there is no demand. Against 1 unit, the probability is 0.50, and similarly against 2 units, your the probability is 0.20. Another assumptions we are making that this is an exhaustive list. That means there is no probability that the demand will be, say, the greater than 2. It's clear. So when you add these 3 probability values, you get a value of 1. As far as lead time is considered, the possible the lead time in days could be either 1 day or 2 days. It cannot be just 3 days or say 4 days or other days. So it is restricted to, say, that just 2 values, 1 or 2. Against 1 day lead time, the probability is 0.75. That means 75% of the cases you may assume the lead time would be 1 day, whereas the remaining 25% of the cases the lead time could be just 2 days. So against 2 days lead time, the corresponding probability is 0.25. Okay. Now from the 2 distribution, it is apparent that the demand during lead time can be as low as 0 and as high as 4. That means supposing the demand is say 0 and the lead time is 1. So what is the demand during lead time is 0. Suppose the demand in both the days, that means maximum the 2 days lead time you have, and there is a possibility, there is a probability that in both the days the demand is 0. So it should be or at the maximum level both the days of say the lead time. That means the first day there could be a demand for 2 units, as well as in the second day there could be a demand for 2 units. That means so the 4 days the 4 units could be the maximum demand during lead time. So the demand of 2 units on each of 2 lead time days, that is 4, and the demand of 0 units, okay, on each of 2 lead time days. So it is varying between 0 and 4. To determine the probability of each given lead time demand, it is necessary to sum the probabilities of the various ways a specific lead time demand can occur, as illustrated below. That means we are actually we are using our say the method of calculating the possible the demand levels as well as the corresponding probabilities, considering the basic say the events and from the first principles. Now the lead time demand is 0. There is a possibility. So how many ways the lead time demand can be 0? The first day there could be 0 demand. There is a possibility of 0 demand, and first day 0 demand, there is a possibility, and the lead time is just 1 day. So what is the possibility that the lead time is 1 day, that is 0.75, and what is the probability that the demand on a particular day is 0 units, that is 0.30. So it is 0.75 into 0.30, that is 0.2250. So we need to consider all possible events leading to this particular condition. Now there could be, the first day there could be 0 demand, there is a probability, and there could be say the 0 demand on the second day. Now why do you consider the 2 days for the demand? Because the lead time could be the 2 days. So what is the probability that the lead time will be 2? That is 2 days, that is 0.25. Already you referred to the table, you get these values. And in the first day the probability is 0.30 and the second day is also 0.30. So you get a value of 0.0225. So you add these two, you get a value of 0.2475. Next one, lead time demand is equals to 1. So we try to compute its probability. So the first day in 3 ways might happen. That means the first day 1 demand, that's all. So 1 day lead time, that is probability is 0.75, and what is the probability? The demand will be 1 unit, that is 0.50. So it is 0.75 into 0.50. Now the other 2 possibilities are the first day 0 demand, the second day 1 demand. So obviously 2 days lead time, that is the probability is 0.25. So first day the demand is 1, probability is 0.30. The second day the demand is say 0, that is the first day it is 0 and the second day it is 1. So this is 0.3 into 0.5. So the total will be 0.0375. Or alternatively, first day there could be 1 demand and the second day there could be 0 demand. And accordingly, you have these probability values. So the 0.25 into 0.50 into 0.30, that means 0.0375. So the total is 0.4500. Then the lead time demand is 2. There is a possibility. So how many ways it can happen? That means just the first day, that is the first possibility. There could be a demand for the 2 units. So this is your lead time. So lead time is 1 day, and during this day the demand is the probability for the 2 units demand is 0.20. So it is 0.1500. Now the other possibilities are first day 0 demand, second day 2 demand, or first day 1 unit demand, second day 1 unit demand, or the fourth possibility is the first day 2 units demanded, the second day obviously 0 units demanded. And but these are the probabilities. That means the lead time is that what is the probability that lead time is 2 days, that is 0.25. So these are 2 days. Everywhere we consider 2 consecutive days. The corresponding probabilities are 0.25, and then the first day 0 demand 0.30, okay, and the second day the demand is say the 2 units, that is 0.20. So similarly we consider all the relevant probability values for 1 unit demand or the 2 units demand, and then when you add all the individual probabilities, okay, then you get the total probability as 0.2425. So you please follow the steps. It is explicitly we have tried to elaborate all the steps, and I hope there is no confusion yourself. Similarly, the similar method we have applied to calculate, or you may apply to calculate the lead time probability for the lead time demand of 3 units. So in the 2 ways it can happen: first day 1 demand, second day 2 demand. first day 2 demand, second day 1 demand. That means the lead time will always be 2 days. So the first day, what is the probability that in the first day that the demand will be 1 unit, that is 0.50, and in the second day what is the probability that the demand will be, say, the 2 units, that is 0.20. And similarly on the second day, what you find that on the first day, so there will be the demand for 2 units, corresponding probability is 0.20, and on the second day there is a probability of the demand of, say, 1 unit, so that probability is 0.50. So when we consider both the possibilities, you get a value of 0.0500 as the probability. And similarly, the lead time, the demand 4, corresponding probabilities, how do you calculate? That is, the first day 2 units demanded, the second day 2 units demanded. So this is the possibility, that is 0.0100, 0.25 into 0.20 into 0.25. So this way we calculate the lead time, the demand, the probabilities. So first we consider what are the possible lead time, demand, the units. In this case there are this demand, lead time demand may vary from 0 to say the 4, and it's a discrete case. So that's why it could be 0 or 1 or 2 or 3 or 4. So that's why the lead time demand, we have used this notation capital M. It varies from 0 to 4, and you may have a lead time demand of 1 unit or 2 units or 3 units also, and the corresponding probability, that is the lead time demand probability, that also we have computed. So when you add all these 5 values of the probabilities, so it becomes 1, and then we add one say the column in this table. So what is this column? This column is essentially probability that M, that means lead time demand, is greater than B. So what is B? B is basically the reorder points. So this notation we use. So you add this column, like here the probability that the lead time demand is greater than the reorder point. So this is a Q system. So the Q system is having 2 important parameters. One is the order quantity and the second one is the reorder point. And depending on the current level of demand, okay, either you place the order or you do not place the order. When you place the order quantity remains same. So that is essentially the Q system. But at what point in time you are required to place the order, that is not known. It all depends on how much the demand is occurring, as well as what is the current inventory position. Okay. So during the lead time, if you find that the demand is greater than the reorder point, right? So obviously there could be a stockout situation, demand, and so this is the probability of going stockout. So what is this probability? That means the lead time demand is, so there will be no say the don't demand, and the corresponding probability is 0.2475. But there is a probability that there could be demand greater than 0. So either 1 or 2 or 3 or 4. So what is that probability? Obviously 1 minus 0.2475, that is 0.7525. Now from 0.7525, if you subtract 0.4500, you get a value of 0.3025. That means when the lead time demand is 1 or greater than 1, what is this probability? Probability is 0.3025. So same say the rule you follow, the same logic you follow, and ultimately against each lead time demand level, corresponding the probability that the lead time, the probability that lead time is greater than the reorder point. So that value you can calculate against each lead time demand level. So these values are given. Obviously, if you have say the the safety stock as 4 units. So what is the probability that there will be stockout probability? This is the stockout probability. So the stockout probabilities obviously will be 0. Whereas if you keep a say the safety stock as 3 units, there is a probability that the probability of 0.01 that there could be a stockout. Okay, so this is the interpretation. So here the problem says that the probability of stockout of 0.20 would require a reorder point of 2 units. This is obviously 0.20. Is it okay? 0.20. That means 0.20. This value lies between 0.30 and 0.06. So obviously you prefer the lower value. That means against this value you get the lead time demand of 2 units. So that should be your say the reorder point. Okay. Now you can use the different types of say the mathematical formulations when you deal with continuous demand distributions, like normal distribution, like say exponential distribution, or say continuous uniform say distribution for the demand or the lead time. Now depending on the types of costs made available and or relevant in a given problem, the problem is formulated. I repeat, that means depending on the types of costs made available. So many a time we are restricted by this condition, and or relevant in a given problem, the problem is formulated. This cost can also be in the form of opportunity cost. So concept of opportunity cost already we have defined. So you please refer to those say the lecture sessions where with examples we have discussed the concept of opportunity cost. We have formed the opportunity cost matrix. Now the objective is to determine order quantity when total relevant cost is minimum. It is in any inventory kind of problem, say or inventory problems of any type, always we try to minimize the total relevant cost. Okay, and so there could be different types of formulation when you deal with continuous demand distribution. So we'll just refer to say some important formulations in this particular case. So the first one is the formulation 1. Given C the cost per unit, that means the item is in the system, item is to be procured or item is to be produced. So you must know that what is the cost incurred per unit. So this value is given to you, this value is known. So given C, that is small c, cost per unit, and Cu, per unit under stock cost. So this is the notation we have used. Determine order quantity X with demand density function Fy for demand Y. Okay. So that means there is a density function and the demand is Y. The demand, the notation is Y. So Y is a random variable. Expected cost corresponding to the order quantity X. So that is EF subscript X is given by EFX equals to C into X plus Cu integration X to infinity Y minus X Fy dy. So this is the expected number of units short under stockout multiplied by say the stockout cost per unit, or sometimes it is referred to as the understock cost per unit. Taking the first derivative with respect to x, x is the decision variable, and setting it to 0, we get these expressions. Okay, so this is cumulative distribution function for x, capital Fx equals to Cu minus C by Cu. So how do you get it? You need to apply the Leibniz rule. That means you need to differentiate an integral function. So obviously, you need to use the well-known the Leibniz rule. So what is Leibniz rule? The derivative of any expression of the form. So this is the form. That means capital Gx is equals to integration hx to kx. So the lower limit of integration and the upper limit of the integration. That means gxy dy. So this is the function. So this is we are explaining the Leibniz rule in general form. So the derivative is given by, that means ddx of gx is equals to these expressions. So you just go through, you study these expression, and you can take up several numerical examples which will help you in applying the Leibniz rule. So this is the partial derivative. This is the first term, partial derivative with respect to x, and these are the changes you make with respect to in the function of say in this function gxy in respect of kx as well as in respect of hx, and then you take the partial derivative with not partial derivative, you take the derivative of say kx with respect to x as well as the derivative of say hx with respect to x. This rule will enable us to differentiate all of the integrals which we need for this kind of inventory problems. So Leibniz rule is widely used. Now this is just one example to understand the applicability, or to understand how the Leibniz rule is used. Let us assume that for the given item, demand is normal with mean of 100, that is the notation is mu, and the standard deviation of 20, and the notation of standard deviation is sigma. C equals to 100 and Cu is 1000. So what is Fx? Capital Fx is 1000 minus 100 by 1000, that is 0.9. Okay, we have already derived this expression. So reference to a standard normal distribution table. So I suggest that you pick up any textbook on the say probability and statistics, and or any textbooks on say the inventory management systems, which we have suggested, and definitely in the appendix you will find the standard normal distribution table is given. Okay, so you must be able to say read this table and how to get these values. So against so from the standard normal distribution table you get a value of z equals to 1.28 against capital Fx of 0.90. Hence the order quantity is x equals to mu plus z into sigma, and this is 100, and this value you get, that is value of z from the standard normal distribution table, that is 1.28 into 20, that is 125.6 approximated as 126 units. This is the next formulation. That means given K0 opportunity cost of 1 unit of overstock and Ku is the opportunity cost of 1 unit of understock. As already we have explained, that entire the problem can be explained in terms of the opportunity cost also. Order quantity is x and y is the demand with its probability density function Fy, like in the previous case. So the expected relevant cost for ordering x units is given by, that means in terms of the opportunity cost. So this is the opportunity cost for 1 unit of overstock, and this is the opportunity cost for 1 unit of understock. So this is 0 to x minus y Fy dy, and similarly for this one this integration x to infinity y minus x fy dy. So this is the case of understocking and this is the case of overstocking. Taking the first derivative with respect to x decision variable and setting it to 0 for minimization of the expected cost, we get these expressions. That means a capital Fx equals to ku by ko plus ku. You can definitely derive this expression. And then what is the equivalent? That means the relationship between the opportunity cost and the total costs are given below. That means ko equals to small c and ku equals to cu minus c. So what you can do that while you formulate the total cost expression, you can also add other relevant costs. So like say, you can add the salvage value. Okay, so the CS, that means per unit basis. If you consider the salvage value cost or the salvage value, it's not a cost, actually it is basically a revenue per unit unused or unsold. The expected cost equation becomes EFX equals to CX. So you need to the cost equation, that's why it's a negative term because it is opposite to cost. So CS into 0 to x, x minus y, this is the overstock amount in fact. So the per unit overstock, you sell it with reduced price obviously. So that is basically called the salvage value. So it is basically this is the inflow of cash, not the outflow of not outflow of money. This is inflow of money. That's why it is a negative one. Okay, and this is your understock cost. So when you apply the Leibniz rule, you get an expression like this. Okay, with the minimum the expected cost. So Fx equals to Cu minus C by Cu into Cs. As it goes, there can be different formulations of the static inventory problem under risk depending on the types of demand distributions we assume and the types of relevant costs we consider. So with this we conclude the session on say the static inventory problem say under risk. So the both the discrete distribution as well as the continuous distribution you need to consider, and I am sure that with those the illustrative examples the concept which you develop, it will help you in the formulating the problem, and there could be different others the inventory problems we will be dealing with, and this the knowledge will help you in the formulating the difficult types of the inventory problems. So thank you.